everyone, welcome back. In this particular video, we will be discussing the problem co-prime numbers. We are given a number n. What we need to do is have to find the count of numbers from 1 to n which are co-prime to n. Now, first let's discuss this word co-prime, then we will come back to the problem statement. Two numbers are said to be co-prime to each other. Let's say co-prime of a comma b is said to be true if the list of common factors, or you can say the common factors among a and b are just only one number, which is 0, or you can say not 0 but 1 itself. That is, common factors among a and b should be only the number 1, not other than that. Or you can say the highest number which is common among them, the highest number which is a factor of both a and b and which is common among them is nothing but 1. Or you can say, when, let's say, take example of 5 and 7. Are 5 and 7 co-prime to each other? What are the factors of 5? Factors of 5 are 1 and 5. That is the numbers which you can divide by 5, or you can say the 5 is a multiple of 1 and 5 both. Similarly, 7 is a multiple of 1 and 7. So what is the common factor among them? 1 is the common factor and it is the highest common also. So we can say, since the highest common factor among 5 and 7 is 1, yes, 5 and 7 are co-prime to each other. This is the definition of co-prime. If I take the numbers, let's say, maybe if we say the first number is 6, the second number is, let's say, 77. How about them? Even if both the numbers are not individually prime, this concept is not related to prime numbers as such. In the first example, you might have thought that if two numbers are prime, then they will be co-prime. No, it is not like that. If you will see what are the factors of 6, it is 1, 2, 3, 6. That is, 6 is a multiple of 1, 6 is a multiple of 2, 6 is a multiple of 3, 6 is a multiple of 4. What about factors of 7? 77, it is having 1 as a factor, it is having 77 as a factor, it is having 7 as a factor, it is having 11 as a factor. Is there any common factor among both the numbers? Yes, 1 is again the common. Is there any other common number? No. So again, since the highest common factor of both these numbers, that is the HCF, highest common factor, or also known as GCD, greatest common divisor, If it is 1, then the numbers are co-prime. Let's also take a test case where the numbers are not co-prime. So if I maybe, let's say, take a test case of 12 and let's say maybe 20. So what are the factors of 12? You will say the factors of 12, or maybe let's not take 20. Let's say the other number is 21. The factors of 12 are 1, then you can say 12 itself, 2, 6, and then it will be 3 and 4. So these will be the factors. Let me just write in one single line. 1, 2, 3, 4, 6, and 12. These will be the highest factors. What about 21? 21 will have a factor 1, 21 itself. Every number have two at least factors, 1 and number itself. Then there will be a factor 3, there will be a factor 7. And I guess these are the only factors possible. Even if there are, we are not concerned with more factors because you can see 3 is common among both. And since 3 is not equivalent to 1, the highest common factor of 12 and 21 is at least 3. And it is not equal to 1. Hence, these numbers are not co-prime. So in this case, yes, they were co-prime. In this case, yes, they were co-prime. But in this case, no, they were not co-prime. Now that we know the definition of co-prime numbers, let's come back to the problem. We are given a number n. We have to find the count of numbers from 1 to n which are co-prime to n. That is, let's take 9 as an input. If n is 9, we have to find how many numbers in the range 1 till 9, 1 till n, which are co-prime with 9 itself. So is a 1 co-prime with 9? What are the factors of 1? It is only having one factor, which is 1 itself. What are the factors of 9? Whatever factors it will be, you can say, since 1 is only having one factor, which is 1, the highest common factor will be 1. GCD of 1, 9 will be 1 only. So answer will be, yes, this 1 is a co-prime number with n. Always for co-prime thing, you have to take a pair, not just a single number. For 9, 2, what are the factors of 9? If I write the factors of 9, it will be 1, then 3, and then 9 itself. What about 2? It is having factors 1 and 2. Again, only 1 is the highest common one. So since GCD of 1, not 1, but 2 and 9 is nothing but 1 only, yes, 2 is also co-prime with 9. So count will become 2. What about 3? If you will take GCD of 3 and 9, then it will be 3 only, because 3 is a common among both of them. So 3 is not a coprime number with n. What about 4? 4 have factors 1, 2, 4. Again, out of them, it is not having anything common apart from the number 1 itself. So since GCD is 1, yes, coprime, the 4 is coprime with n. That is, the count will become 3. 1 is coprime, 2 is coprime, 4 is coprime. We just have to count the number of coprime numbers from 1 to n, which are coprime with the number n. N will be in the input. What about 5? 5 will be coprime also, because the highest common factor will be 1. What about 6? 6 will not be a coprime number, because 6 and 9 both have a GCD which is 3. Or you can say highest common factor among them, HCF, is 3. 5 was, 6 is not. What about 7? 7 will also not, actually 7 will be, because 7 will have only one factor common with the 9, which is 1 itself. What about 8? 8 will be again, because it is only having a factor which is 1 common. Finally, for 9, obviously a number will never be coprime with itself. Apart from number 1 with 1, you can say, if you will take GCD of 9 with 9, it is obviously going to be 9. Highest common factor in 9 and 9 is 9 only. So it is not coprime with itself. So having said that, how many numbers are coprime with 9 in range 1 to n? The first number, this is the second number, then 4 is the third number, 5 is the fourth number, then 7, and then 8. So output should be 6. As you can see, the output is 6. These are the numbers. We don't have to print those numbers, but what can be the approach to solve this? See, in order to check which numbers are coprime with the number, we have to find factors. So one brute force solution can be just list down all the factors of all the numbers from 1 to n. That is, create a list of factors of 1, which will be 1, list of factors of 2, which will be 1 comma 2, list of factors of 3, which will be 1 comma 3. And how will you find the list of factors? By keep on dividing that number by every other number smaller than that. That is, in order to find factors of, let's say, 8, what will you do is run a loop from 1 till 8 and check, is 1 dividing 8? Yes, 1 is a factor of 8. Is 2 dividing 8? Yes, 2 is a factor of 8. Is 3 dividing 8? No. And how to check whether it is divisible? You can check by modulus operation. 8 modulus 2 will give you 0, but 8 modulus 3 will not give you 0. This is how you will check whether 2 is a factor of 8 or not, 3 is a factor of 8 or not. So once you know the factors of each and every number, 8 is having factors 1, 2, 4, and 8. Using that list, you can just find, is there any number in this list apart from 1, which is also present in this list. So brute force will be to first find the list of factors. And in order to find the list of factors, you will have to run a loop till that number. If number is 8, you will have to run a loop for 8 times. And since you have to run it for all n numbers, it will be n times n. That is, finding the factors of one number will be n. Finding the factors for n such numbers will be n times n. That is, you can say n square overall. And then finding common, we are assuming you will find it in constant time, provided that this list of numbers, the list of factors, you are storing in a set data structure or a hash set data structure. But still, n square is a very poor time complexity, provided that we can do better in terms of time and also in terms of space. We don't need to store all the factors of a given number. So how we can do it better? We will be thinking in terms of GCD only, but without actually finding all the factors of a number. So that is, instead of listing down all the factors of 9, which is 1, 3, 9, similarly listing all the factors of 8, 7, 6, what we will do is we will find the GCD on the go. That is, find GCD of 1, 9, is it 1 or not? Find GCD of 2, 9, is it 1 or not? Find GCD of 3, 9, is it 1 or not? So how to find GCD of two numbers? That is the next concept. Let me take two numbers as maybe the numbers which is 16 and let's say 30. And we need to find out what is the GCD among them. So we will be finding GCD of two numbers using Euclidean algorithm. You might know it already. If you don't know it, then it is nothing but long division, which you might have done in your elementary school mathematics. So when we say what do you mean by long division, or how do you find the GCD of two numbers using long division? You will take one of the numbers as a numerator, you will take another number as a denominator, and keep on dividing till the denominator reaches 0. That is, if this is divisor, this is the dividend, or actually this is dividend, this is divisor. Till the point divisor does not reach 0, we will keep on dividing, because we can't divide by 0. So if you will try to divide 16 by 30, you won't be able to even take out 1 as a quotient. Entire 16 will come as a remainder, or you can say the 16 is nothing but remainder. When you divide 16 by 30, what is the remainder? It is 16. That remainder is going to become the new denominator, and the previous denominator is going to become the new numerator, and we again have to divide. That is, at this point of time, you are just swapping the variables. If numerator is smaller than denominator, you can't divide. It will not get divided. But at the very next step, what you are doing is making the remainder become the new denominator, making the previous denominator become numerator. And this time, if you will divide, you will say 16 times 1 is 16. Subtract it, you will get the remainder as 14, because the 30 modulus 16 is nothing but 14. Now, since this remainder is not also 0, we will again do division. Remainder will become the denominator, previous denominator will become the numerator. Is this time, if you will try to divide 16 by 14, 16 modulus 14 will give you what? It will give you 2 as a remainder. That is, if you will subtract 14 from it, 2 will be the remainder. Again, it is not done. The division will still continue. Remainder will be the new denominator. Previous denominator will become the new numerator. And if you will this time divide 14 by 2, you will get 7 as a quotient. However, we don't care about quotient. You will say 14 modulus 2 is nothing but 0. And at this time, if you will just subtract 14 from it, that is 7 times 2, 0 will be the remainder. It will become new denominator. The previous denominator will become new numerator. But as soon as you are dividing by 0, you will have to stop. And what is the answer? The answer of 30, 16, the GCD of them is nothing but 2 only. So as soon as the denominator reaches 0, the numerator is the answer. If let's say this is the variable a, let's say this is the variable b, how we are finding the GCD of a comma b? How we are finding the GCD of numerator comma denominator? We are saying in the next step, first parameter we are taking as numerator, second parameter we are taking as denominator. In the next step, what is happening? What is the new numerator? It is the previous denominator. That is, first parameter will be the previous second parameter, that is b. B is going to become A now, the new numerator, new A. And what about new B, the new denominator? It will be the remainder when we divide A by B, that is A modulus B. So we have to do a recursive call, that is, we have to do recursion. You can also do it using iteration, but recursion will be only of 2 lines of code. GCD of A comma B will be same as GCD of B comma A modulus B. Keep on doing it till the base case. What should be the base case? The base case should be when the denominator reaches 0. That is the second parameter, B reaches 0. In such a case, if B is reaching 0, what is the answer? What is the GCD? Now we know the answer, which is the A. That is the numerator is the answer. And why is this actually Euclidean's algorithm working? Because GCD of 16, 30 is the same as GCD of 30, 16 is the same as GCD of 16, 14 is the same as GCD of 14, 2, which is equivalent to 2. So all these pairs which we are having in the long division are having the same GCD. That's why we are able to make these recursive calls. That is, GCD of A, B is the same as GCD of B, A modulus B. The GCD of two numbers where one number is treated as numerator, other number treated as denominator is same as GCD of previous denominator becoming new numerator and the division's remainder becoming the new denominator. So what is the time complexity to calculate GCD of two numbers? It is nothing but order of log of minimum of A comma B, where minimum of A comma B in this example will be 16. It will never go. The GCD of two numbers can never become more than the smaller number. GCD of 16, 30 can never become more than 16. So having said that, we know how to do GCD. It is just 2 lines of code. One line will be recursive call, another line will be the base case. In logarithmic time, we know how to find GCD. We have to find GCD for n times. That is GCD of 1, n, 2, n, 3, n, 4, n, up till n, n. Provided that each GCD operation will take log n time. However, it will be log 1, log 2, log 3, and so on. But in general, you can assume worst case as log n. For finding GCD for one time, we are doing GCD n times. Overall time complexity in doing the Euclid's algorithm, the optimized solution, finally we can say it is n times log n, which is better than brute force because brute force was n square. It is n log n. What about the space complexity? We will be using recursion. Recursion will take log n space because since the number of times we are doing division are also getting accounted in the function call stack, space will be log n because at one point of time you will find GCD of only one pair. not all the GCDs. In stack, there will be only one function in at a point, that is GCD of either 8, 9 or 7, 9. Only one of the GCD functions will be in the stack. So space will be only log n, not n log n, but only log n is almost constant because n will be very small. As you can see, n will be only 1000. So log of 1000 is very, very small value. So you can still consider space to be constant. So it is not that you are actually wasting space to optimize time. No, you are optimizing time with taking a very extra little space. Now that we know the optimized solution, we will write the instruction manual using it. So for that, what we are doing is we are running a loop to count how many numbers are co-prime with n, running a loop from 1 till n, and checking what is the GCD of those numbers. So check GCD of the loop variable, let's say index of index and n is a 1 or not. If GCD is 1, then the numbers are co-prime. If GCD comes out to be 1, we can say that increment the count. We will maintain the count because we only have to print the number of co-prime numbers. So initialize the count as 0, and whenever we find a co-prime number, that is whenever we find GCD as 1, increment count by 1. Increment count by 1. And finally, we will have to just return the count variable. But the point is, how will we do the GCD? How will we find the GCD? So for that, we will be creating a recursive function, which will take two numbers for which we want to find the GCD. And the recursive call will be that the GCD of A and B will be same as GCD of, you can say, recursive call will be the pair A comma B will be having the GCD same as pair B comma A modulus B. So make a recursive call. But before making recursive call, check whether it is a base case. And what is the base case? If the denominator, that is the second parameter, is 0, then numerator is the answer. So return A. Otherwise, return the same thing. That is whatever we are getting from recursive call, that is our answer also. Whatever GCD of 14 comma 2 is, that is the GCD of 16 comma 14. That is the GCD of 30 comma 16. That is the GCD of 16 comma 30. So just return whatever we are getting. So 2 lines of GCD and almost 4 to 5 lines of the coprime logic. And we will be writing the code in Java programming language. We have already discussed how to find coprime numbers, or how to check whether two numbers are coprime using the logic of GCD, whether GCD is 1 or not. So if you have not watched the first video where we discussed how to find GCD, how to check whether two numbers are coprime, first you will have to watch it. It is a prerequisite. Then only the code will be easy to understand. So in order to find the GCD, first let's complete the GCD function. We are using a recursive function so that there is only 2 lines of code. First will be the recursive call, that is GCD of A comma B will be same as GCD of B comma A modulus B. That is previous denominator will become new numerator, and the remainder operation A modulus B modulus operator will become the new denominator. And we are doing long division till the point denominator reaches 0, till the point B is not 0. As soon as B is the 0 value, that is a base case, we have to return numerator as the answer. That we discuss using a test case of 16 comma 30. So this is a 2 lines of GCD function. Now we know how to find GCD of two numbers. We can also check coprime. That is, initialize the coprime as 0, the count as 0, and run a loop because we have to check from each number 1 to n whether it is coprime to n or not. So run a loop from index 1 till equal to n, less than equal to n, index plus plus, and do what? And check if the GCD of what? Of the current index with the n variable is 1 or not. If GCD is 1, yes, increment the count. And if it is so, then what we can do is we can return the count variable. So first we will try to run it for the sample test case. That is for 9. We discussed how many numbers are co-prime with 9. There are 5 such numbers, actually 6 such numbers. 1, 2, 4, 5, 7, 8. These are the numbers. 6 is the output. How about taking corner scenarios? If n is 1, if n is 1000, let's take n as 1. So for 1, I don't think there will be any other number which is co-prime with 1 except 1. So our output should be 1. Yes, 1 is co-prime with 1 only. How about 1000? Let's see for 1000 how it will give or what output it will give. Maximum output can be 1000 only, but obviously it will not be 1000. It will be lesser than that. Let's see. As you can see, there are 400, exactly 400 such numbers. Let's now submit and see if it is going to work for all the test cases. including the corner ones or not by submitting it. So as you can see, it is working for all the test cases. With that, we are done with the problem coprime numbers. The time complexity, before ending the video, let's discuss. Since we are first of all running a loop on n size array, or not a array, but a n size loop, or you can say loop from 1 to n, which is taking linear time, order of n time. But inside that, if you think there are just if conditions, so time complexity is constant, then you're wrong. Why? Because inside the if condition, we are calling a function which is GCD of two numbers. And GCD of two numbers is a Euclidean algorithm, which we can find out in the GCD as log of minimum of a comma b, where a and b are the numbers for which we have to find the GCD. In uh, worst case, you can assume the GCD as log of n, where n can be the minimum of them. So since each GCD function will take log n time, you're doing GCD n times, overall time complexity will be n log n. And what about the space complexity? Space complexity is not due to the coprime logic, but it is due to the GCD logic, because we are doing recursion. Recursion means we are doing the recursion call stack space. We are using the function stack space, which is going to take log n space. For each GCD operation, worst case can be log n number of function calls. So space is only log n, but time is n log n, which is better than brute force. The follow-up problem will be to try to think it in terms of other solutions or even better solutions. There is a mathematics-based solution which is using Euler's theorem, which can do it in even lesser time. But that is not a first of all easy thing to do. So as a beginner, treat this solution as the most optimized one, but try to solve similar problems with similar concepts based on coprime logic, based on GCD logic, which will be given in the problem description. Till then, bye bye, take care. Let's meet in a new video with a new problem.